Thank you very much for your attendance. Firstly, I will introduce myself. My name is Alberto Tapetado. I'm working as a PhD student at University Carlos III of Madrid in Electronic Technology Department. Our research interests include silicon polymer, optical fiber sensor, and WDM sensor network. In this presentation, I'm going to show you a brief description of my last work, titled WDM Sensor Network Approach, Bridging the Gap Toward POF-Based Photonic Sensing. Firstly, I would like to show you the different sections that I'm going to follow to understand the main concept about the WDM sensor that we propose. I will start talking about the introduction, then I will continue talking about the polymer fiber Bragg rating, operation principle, and finally the results. I will finish talking about the conclusion and the future works. The number of fiber optic sensors for biomedical application is increasing, and the ability to monitor patients without medical assistance is of great interest. Historically, the first application of fiber optics was the illumination of internal organs during the endoscopy procedures. Nowadays, there are different medical areas where fiber optics hold enormous potential. For example, there is the need to develop fiber optic sensor for minimal invasive surgery processes. The most important features include the lightweight, the smart height, the geometrical flexibility, and the electrical and thermal isolation. For this reason, I want to propose you the following question. Why not intensity-based optical biosensor made of polymer optical fiber? It's clear that the polymer optical fiber are very attracted to be explored in biomedical application because they are made of biocompatible material compared with silica. Other important features include the simplicity of implementation, the lower price of the fiber, and the good mechanical properties. The main drawback about the intensity fiber optic sensor is the need of a self-reference system in order to avoid false reading caused by the fluctuation of the light source. On the other hand, it's very important the fiber link between the remote sensing area and the monitor unit. The fiber optic link should be suitable for the source reads and in building network. In addition, the fiber optic link will be suitable for medium range distance with application in interhospital network, or to provide a connection between the patient's home and the hospital in telemedicine applications. Although the polymer optical fiber are a low-cost solution for the short-reach network, the high attenuation of the fiber limit the maximum length. For this reason, other solution is an hybrid polymer optical fiber silica topology. But the main drawback about the main reason behind this lack of development is the mismatch between the optimum operating wavelength of the polymer optical fiber and the optical device explored for telecommunication purposes. To overcome this problem, the microstructural polymer optical fiber try to take advantage of the benefits of polymer optical fibers and while maintaining the possibility to inscribe fiber Bragg rating in the C or L band, used for telecommunication purposes. A few mode microstructural polymer optical fiber are used in each remote sensing points. These fibers are formed by 3 rings of hole around the core, and the core and cladding diameter is 15 and 150 microns. The attenuation is 0.82 dB per centimeter. Only 2 sensors are evaluated in this schematic, but we can use more sensors. Their sensor wavelengths are 1525 nanometers for the first sensor and 15 and 50 nanometers for the second sensor. Their reflectivities are 27 and 38%. In this slide, I want to show you the hybrid silica microstructural polymer optical fiber topology that we propose. A broadband light source is externally modulated at a specific frequency by a acousto-optic modulator in order to reduce the system noise. The result signal is launched into the remote sensing area by a broadband circulator. Each remote sensing area consists of a microstructural polymer optical fiber placed before the fiber optic sensor and a referencing silica fiber Bragg grating placed before the WDM device. The reflected signal don't overlap in wavelength, and both reflected signals are used to calculate the source reference parameter. At the realization stage, a virtual phase shift are applied to the modulator signals at the reference and sensing channel in order to offer more flexibility to the user, for example, to get more linearity or more sensitivity in the system response. A virtual locking amplifier are used to interrogate all available sensors and to calculate the source reference parameter. The source reference parameter are defined as the output voltage ratio at the realization state for different value of a virtual phase shift for the reference and sensing channel. The calibration curves for the first and second sensor are shown in this figure. A variable optical attenuator, a single mode variable optical attenuator, is used to simulate the each fiber optic sensor. Different phase shifts are used to obtain different system response with a high linearity, a high sensitivity, and the output the self-reference parameter are measured for different modulation loss of each sensor. This figure also shows the crosstalk used to evaluate the possible interference between adjacent channels during the measuring. In the upper figure, different measurement parameters, different measurement self-reference parameters are taken for different modulation loss. The same similar results are obtained when monitoring the second sensor. In both cases, no crosstalk is detected, so the sensor can be interrogated simultaneously without mutual interference. The source reference property is evaluated introducing attenuation in the input light source by a single mode variable optical attenuator. The virtual phase shifts are fixed at a specific angular frequency during the measuring, and different modulation loss are measuring. This figure shows that no change in the source reference parameter are detected, and after inducing 10 dB of attenuation. Finally, I would like to show you the conclusion that we obtained for this topology. Firstly, the application of this topology is obviously the biomedical applications. The self-reference optical intensity sensor network is a combination of a polymer optical fiber and silica-based optical component compatible with a WDM network. An extra power margin greater than the dB is used to reach larger distances, and a virtual instrumentation environment provides flexibility and easy reconfigurability. Finally, I would like to show you that this topology can be improved with a real test with an optical intensity sensor for biomedical application, for example, to the chest respiratory sensor. And finally, we can improve the sensor loss of the connectorization of the polymer optical fiber Bragg rating in order to reach larger distances. Finally, I would like to thank the funding of my research to the Spanish Ministry of Economy and COS-Action and Symphoton. And I would like to thank also the Display and Photonic Application Groups and Aston Institute of Photonic Technology to share with me their knowledge, especially Professor David Webb. Finally, I would like to thank you for your attention. Thank you very much.